A Stirling engine is a heat engine that operates by cyclic compression and expansion of air or other gas, the working fluid, at different temperatures, such that there is a net conversion of heat energy to mechanical work. More specifically, the Stirling engine is a closed-cycle regenerative heat engine with a permanently gaseous working fluid. Closed cycle, in this context, means a thermodynamic system in which the working fluid is permanently contained within the system, and regenerative describes the use of a specific type of internal heat exchanger and thermal store, known as the regenerator. The inclusion of a regenerator differentiates the Stirling engine from other closed-cycle hot air engines. Originally conceived in 1816 as an industrial prime mover to rival the steam engine, its practical use was largely confined to low-power domestic applications for over a century. Stirling engines have a high efficiency compared to steam engines, being able to reach 50% efficiency. They are also capable of quiet operation and can use almost any heat source. The heat energy source is generated external to the Stirling engine rather than by internal combustion as with the Otto cycle or diesel cycle engines. Because the Stirling engine is compatible with alternative and renewable energy sources, it could become increasingly significant as the price of conventional fuels rises, and also in light of concerns such as depletion of oil supplies and climate change. This type of engine is currently generating interest as the core component of micro-combined heat and power (CHP) units, in which it is more efficient and safer than a comparable steam engine. However, it has a low power-to-weight ratio, rendering it more suitable for use in static installations where space and weight are not at a premium. Name and classification. Robert Stirling was a Scottish minister who invented the first practical example of a closed-cycle air engine in 1816, and it was suggested by Fleming Jenkin as early as 1884 that all such engines should therefore generically be called Stirling engines. This naming proposal found little favour, and the various types on the market continued to be known by the name of their individual designers or manufacturers, e.g., Riders, Robinsons, or Heinrichs, hot air engine. In the 1940s, the Philips company was seeking a suitable name for its own version of the air engine, which by that time had been tested with working fluids other than air, and decided upon Stirling engine in April 1945. However, nearly 30 years later, Graham Walker still had cause to bemoan the fact such terms as hot air engine remained interchangeable with Stirling engine, which itself was applied widely and indiscriminately, a situation that continues. Like the steam engine, the Stirling engine is traditionally classified as an external combustion engine, as all heat transfers to and from the working fluid take place through a solid boundary heat exchanger, thus isolating the combustion process and any contaminants it may produce from the working parts of the engine. This contrasts with an internal combustion engine where heat input is by combustion of a fuel within the body of the working fluid. Most of the many possible implementations of the Stirling engine fall into the category of reciprocating piston engine. History. Invention and early development. The Stirling engine, or Stirling's air engine as it was known at the time, was invented and patented in 1816. It followed earlier attempts at making an air engine but was probably the first put to practical use when, in 1818, an engine built by Stirling was employed pumping water in a quarry. The main subject of Stirling's original patent was a heat exchanger, which he called an economizer for its enhancement of fuel economy in a variety of applications. The patent also described in detail the employment of one form of the economizer in his unique closed-cycle air engine design, in which application it is now generally known as a regenerator. Subsequent development by Robert Stirling and his brother James, an engineer, resulted in patents for various improved configurations of the original engine, including pressurization, which by 1843, had sufficiently increased power output to drive all the machinery at a Dundee iron foundry. Though it has been disputed, it is widely supposed that the inventors' aims were not only to save fuel but also to create a safer alternative to the steam engines of the time, whose boilers frequently exploded, causing many injuries and fatalities. The need for Stirling engines to run at very high temperatures to maximize power and efficiency exposed limitations in the materials of the day, and the few engines that were built in those early years suffered unacceptably frequent failures, albeit with far less disastrous consequences than boiler explosions. For example, the Dundee Foundry engine was replaced by a steam engine after 3 hot cylinder failures in 4 years. Later 19th century. Subsequent to the replacement of the Dundee Foundry engine, there is no record of the Stirling brothers having any further involvement with air engine development, and the Stirling engine never again competed with steam as an industrial-scale power source. Steam boilers were becoming safer and steam engines more efficient, thus presenting less of a target for rival prime movers. However, beginning about 1860, smaller engines of the Stirling/hot air type were produced in substantial numbers for applications in which reliable sources of low to medium power were required, such as pumping air for church organs or raising water. These smaller engines generally operated at lower temperatures so as not to tax available materials, and so were relatively inefficient. Their selling point was that unlike steam engines, they could be operated safely by anybody capable of managing a fire. Several types remained in production beyond the end of the century, but apart from a few minor mechanical improvements, the design of the Stirling engine in general stagnated during this period. 20th century revival. During the early part of the 20th century, the role of the Stirling engine as a domestic motor was gradually taken over by electric motors and small internal combustion engines. By the late 1930s, it was largely forgotten, only produced for toys and a few small ventilating fans. Around that time, Philips was seeking to expand sales of its radios into parts of the world where grid electricity and batteries were not consistently available. Philips management decided that offering a low-power portable generator would facilitate such sales and asked a group of engineers at the company's research lab in Eindhoven to evaluate alternative ways of achieving this aim. After a systematic comparison of various prime movers, the team decided to go forward with the Stirling engine, citing its quiet operation, both audibly and in terms of radio interference, and ability to run on a variety of heat sources. Common lamp oil, cheap and available everywhere, was favored. They were also aware that, unlike steam and internal combustion engines, virtually no serious development work had been carried out on the Stirling engine for many years, and asserted that modern materials and know-how should enable great improvements. By 1951, the 180/200W generator set designated MP1002CA, known as the bungalow set, was ready for production and an initial batch of 250 was planned, but soon it became clear that they could not be made at a competitive price. Additionally, the advent of transistor radios and their much lower power requirements meant that the original rationale for the set was disappearing. Approximately 150 of these sets were eventually produced. Some found their way into university and college engineering departments around the world, giving generations of students a valuable introduction to the Stirling engine. In parallel with the bungalow set, Philips developed experimental Stirling engines for a wide variety of applications and continued to work in the field until the late 1970s, but only achieved commercial success with the reversed Stirling engine cryocooler. However, they filed a large number of patents and amassed a wealth of information, which they licensed to other companies and which formed the basis of much of the development work in the modern era. In 1996, the Swedish Navy commissioned 3 Gotland-class submarines. On the surface, these boats are propelled by marine diesel engines. However, when submerged, they use a Stirling-driven generator developed by Swedish shipbuilder Kockums to recharge batteries and provide electrical power for propulsion. A supply of liquid oxygen is carried to support burning of diesel fuel to power the engine. Stirling engines are also fitted to the Swedish Södermanland-class submarines, the Archer-class submarines in service in Singapore and, license built by Kawasaki Heavy Industries for the Japanese SRY-class submarines. In a submarine application, the Stirling engine offers the advantage of being exceptionally quiet when running. Stirling engines are frequently used in the dish version of concentrated solar power systems. A mirrored dish similar to a very large satellite dish directs and concentrates sunlight onto a thermal receiver, which absorbs and collects the heat and using a fluid transfers it into the Stirling engine. The resulting mechanical power is then used to run a generator or alternator to produce electricity. Stirling engines are forming the core component of micro-combined heat and power (CHP) units, as they are more efficient and safer than a comparable steam engine. CHP units are being installed in people's homes. Functional description. The engine is designed so the working gas is generally compressed in the colder portion of the engine and expanded in the hotter portion, resulting in a net conversion of heat into work. An internal regenerative heat exchanger increases the Stirling engine's thermal efficiency compared to simpler hot air engines lacking this feature. Key components. As a consequence of closed-cycle operation, the heat driving a Stirling engine must be transmitted from a heat source to the working fluid by heat exchangers and finally to a heat sink. A Stirling engine system has at least one heat source, one heat sink and up to 5 heat exchangers. Some types may combine or dispense with some of these. Heat source. The heat source may be provided by the combustion of a fuel and, since the combustion products do not mix with the working fluid and hence do not come into contact with the internal parts of the engine, a Stirling engine can run on fuels that would damage other engines types' internals, such as landfill gas, which may contain siloxane, which can deposit abrasive silicon dioxide in conventional engines. Other suitable heat sources include concentrated solar energy, geothermal energy, nuclear energy, waste heat, and bioenergy. If solar power is used as a heat source, regular solar mirrors and solar dishes may be utilized. The use of Fresnel lenses and mirrors has also been advocated, for example in planetary surface exploration. Solar-powered Stirling engines are increasingly popular as they offer an environmentally sound option for producing power, while some designs are economically attractive in development projects. Heater/hot side heat exchanger. In small, low-power engines this may simply consist of the walls of the hot space, but where larger powers are required a greater surface area is needed to transfer sufficient heat. Typical implementations are internal and external fins or multiple small bore tubes. Designing Stirling engine heat exchangers is a balance between high heat transfer with low viscous pumping losses, and low dead space, unswept internal volume. Engines that operate at high powers and pressures require that heat exchangers on the hot side be made of alloys that retain considerable strength at high temperatures and that don't corrode or creep. Regenerator. In a Stirling engine, the regenerator is an internal heat exchanger and temporary heat store placed between the hot and cold spaces such that the working fluid passes through it first in one direction then the other, taking heat from the fluid in one direction, and returning it in the other. It can be as simple as metal mesh or foam, and benefits from high surface area, high heat capacity, low conductivity, and low flow friction. Its function is to retain within the system that heat that would otherwise be exchanged with the environment at temperatures intermediate to the maximum and minimum cycle temperatures, thus enabling the thermal efficiency of the cycle, though not of any practical engine, to approach the limiting Carnot efficiency. The primary effect of regeneration in a Stirling engine is to increase the thermal efficiency by recycling internal heat that would otherwise pass through the engine irreversibly. As a secondary effect, increased thermal efficiency yields a higher power output from a given set of hot and cold end heat exchangers. These usually limit the engine's heat throughput. In practice, this additional power may not be fully realized, as the additional dead space, unswept volume, and pumping loss inherent in practical regenerators reduces the potential efficiency gains from regeneration. The design challenge for a Stirling engine regenerator is to provide sufficient heat transfer capacity without introducing too much additional internal volume, dead space, or flow resistance. These inherent design conflicts are one of many factors that limit the efficiency of practical Stirling engines. A typical design is a stack of fine metal wire meshes, with low porosity to reduce dead space, and with the wire axis perpendicular to the gas flow to reduce conduction in that direction and to maximize convective heat transfer. The regenerator is the key component invented by Robert Stirling, and its presence distinguishes a true Stirling engine from any other closed-cycle hot air engine. Many small toy Stirling engines, particularly low-temperature difference (LTD) types, do not have a distinct regenerator component and might be considered hot air engines. However, a small amount of regeneration is provided by the surface of the displacer itself and the nearby cylinder wall, or similarly the passage connecting the hot and cold cylinders of an alpha configuration engine. Cooler/cold side heat exchanger. In small, low-power engines, this may simply consist of the walls of the cold space, but where larger powers are required, a cooler using a liquid like water is needed to transfer sufficient heat. Heat sink. The larger the temperature difference between the hot and cold sections of a Stirling engine, the greater the engine's efficiency. The heat sink is typically the environment the engine operates in, at ambient temperature. In the case of medium to high power engines, a radiator is required to transfer the heat from the engine to the ambient air. Marine engines have the advantage of using the cool ambient sea, lake, or river water, which is typically cooler than ambient air. In the case of combined heat and power systems, the engine's cooling water is used directly or indirectly for heating purposes, raising efficiency. Alternatively, heat may be supplied at ambient temperature and the heat sink maintained at a lower temperature by such means as cryogenic fluid, see liquid nitrogen economy, or iced water. Displacer. The displacer is a special-purpose piston, used in beta and gamma type Stirling engines, to move the working gas back and forth between the hot and cold heat exchangers. Depending on the type of engine design, the displacer may or may not be sealed to the cylinder, i.e. it may be a loose fit within the cylinder, allowing the working gas to pass around it as it moves to occupy the part of the cylinder beyond. Configurations. There are three major types of Stirling engines, that are distinguished by the way they move the air between the hot and cold areas. The alpha configuration has two power pistons, one in a hot cylinder, one in a cold cylinder, and the gas is driven between the two by the pistons. It is typically in a V formation with the pistons joined at the same point on a crankshaft. The beta configuration has a single cylinder with a hot end and a cold end, containing a power piston and a displacer that drives the gas between the hot and cold ends. It is typically used with a rhombic drive to achieve the phase difference between the displacer and power pistons, but they can be joined 90 degrees out of phase on a crankshaft. The gamma configuration has two cylinders, one containing a displacer, with a hot and a cold end, and one for the power piston. They are joined to form a single space with the same pressure in both cylinders. The pistons are typically in parallel and joined 90 degrees out of phase on a crankshaft. Alpha configuration operation. An alpha Stirling contains two power pistons and separate cylinders, one hot and one cold. The hot cylinder is situated inside the high-temperature heat exchanger and the cold cylinder is situated inside the low-temperature heat exchanger. This type of engine has a high power-to-volume ratio but has technical problems because of the usually high temperature of the hot piston and the durability of its seals. In practice, this piston usually carries a large insulating head to move the seals away from the hot zone at the expense of some additional dead space. The crank angle has a major effect on efficiency, and the best angle frequently has to be found experimentally. An angle of 90 degrees frequently locks. The following diagrams do not show internal heat exchangers in the compression and expansion spaces, which are needed to produce power. A regenerator would be placed in the pipe connecting the two cylinders. Beta configuration operation. A beta Stirling has a single power piston arranged within the same cylinder on the same shaft as a displacer piston. The displacer piston is a loose fit and does not extract any power from the expanding gas, but only serves to shuttle the working gas between the hot and cold heat exchangers. When the working gas is pushed to the hot end of the cylinder, it expands and pushes the power piston. When it is pushed to the cold end of the cylinder, it contracts, and the momentum of the machine, usually enhanced by a flywheel, pushes the power piston the other way to compress the gas. Unlike the alpha type, the beta type avoids the technical problems of hot moving seals, as the power piston is not in contact with the hot gas. Again, the following diagrams do not show any internal heat exchangers or a regenerator, which would be placed in the gas path around the displacer. If a regenerator is used in a beta engine, it is usually in the position of the displacer and moving, often as a volume of wire mesh. Gamma configuration operation. A gamma Stirling is simply a beta Stirling in which the power piston is mounted in a separate cylinder alongside the displacer piston cylinder, but is still connected to the same flywheel. The gas in the two cylinders can flow freely between them and remains a single body. This configuration produces a lower compression ratio because of the volume of the connection between the two, but is mechanically simpler and often used in multi-cylinder Stirling engines. Other types. Other Stirling configurations continue to interest engineers and inventors. The rotary Stirling engine seeks to convert power from the Stirling cycle directly into torque, similar to the rotary combustion engine. No practical engine has yet been built, but a number of concepts, models, and patents have been produced, such as the quasi-turbine engine. A hybrid between piston and rotary configuration is a double-acting engine. This design rotates the displacers on either side of the power piston. In addition to giving great design variability in the heat transfer area, this layout eliminates all but one external seal on the output shaft and one internal seal on the piston. Also, both sides can be highly pressurized as they balance against each other. Another alternative is the fluidine engine, fluidine heat pump, which uses hydraulic pistons to implement the Stirling cycle. The work produced by a fluidine engine goes into pumping the liquid. In its simplest form, the engine contains a working gas, a liquid, and two non-return valves. The ring bomb engine concept, published in 1907, has no rotary mechanism or linkage for the displacer. This is instead driven by a small auxiliary piston, usually a thick displacer rod, with the movement limited by stops. The two-cylinder Stirling with Ross yoke is a two-cylinder Stirling engine, positioned at 0 degrees, not 90 degrees, connected using a special yoke. The engine configuration/yoke setup was invented by Andy Ross. The Franket engine is a double-acting engine invented by Charles Louis Felix Franket, d. in the 19th century. A double-acting engine is one in which both sides of the piston are acted upon by the pressure of the working fluid. One of the simplest forms of a double-acting machine, the Franket engine consists of two pistons and two cylinders and acts like two separate alpha machines. In the Franket engine, each piston acts in two gas phases, which makes more efficient use of the mechanical components than a single-acting alpha machine. However, a disadvantage of this machine is that one connecting rod must have a sliding seal at the hot side of the engine, which is difficult when dealing with high pressures and temperatures. Free piston Stirling engines. Free piston Stirling engines include those with liquid pistons and those with diaphragms as pistons. In a free piston device, energy may be added or removed by an electrical linear alternator, pump or other coaxial device. This avoids the need for a linkage, and reduces the number of moving parts. In some designs, friction and wear are nearly eliminated by the use of non-contact gas bearings or very precise suspension through planar springs. 4 basic steps in the cycle of a free piston Stirling engine are: the power piston is pushed outwards by the expanding gas, thus doing work. Gravity plays no role in the cycle. The gas volume in the engine increases and therefore the pressure reduces, which causes a pressure difference across the displacer rod to force the displacer towards the hot end. When the displacer moves, the piston is almost stationary and therefore the gas volume is almost constant. This step results in the constant volume cooling process, which reduces the pressure of the gas. The reduced pressure now arrests the outward motion of the piston and it begins to accelerate towards the hot end again, and by its own inertia, compresses the now cold gas, which is mainly in the cold space. As the pressure increases, a point is reached where the pressure differential across the displacer rod becomes large enough to begin to push the displacer rod, and therefore also the displacer, towards the piston, and thereby collapsing the cold space and transferring the cold, compressed gas towards the hot side in an almost constant volume process. As the gas arrives in the hot side, the pressure increases and begins to move the piston outwards to initiate the expansion step as explained in 1. In the early 1960s, W.T. Bale invented a free piston version of the Stirling engine to overcome the difficulty of lubricating the crank mechanism. While the invention of the basic free piston Stirling engine is generally attributed to Bale, independent inventions of similar types of engines were made by E. H. Cook Yarborough and C. West at the Harwell Laboratories of the Yukon. G. M. Benson also made important early contributions and patented many novel free piston configurations. The first known mention of a Stirling cycle machine using freely moving components is a British patent disclosure in 1876. This machine was envisaged as a refrigerator, i.e., the reversed Stirling cycle. The first consumer product to utilize a free piston Stirling device was a portable refrigerator manufactured by Twin Bird Corporation of Japan and offered in the US by Coleman in 2004. Flat Stirling engine. Design of the flat double-acting Stirling engine solves the drive of a displacer with the help of the fact that areas of the hot and cold pistons of the displacer are different. The drive does so without any mechanical transmission. Using diaphragms eliminates friction and need for lubricants. When the displacer is in motion, the generator holds the working piston in the limit position, which brings the engine working cycle close to an ideal Stirling cycle. The ratio of the area of the heat exchangers to the volume of the machine increases by the implementation of a flat design. Flat design of the working cylinder approximates thermal process of the expansion and compression closer to the isothermal one. The disadvantage is a large area of the thermal insulation between the hot and cold space. Thermoacoustic cycle. Thermoacoustic devices are very different from Stirling devices, although the individual path traveled by each working gas molecule does follow a real Stirling cycle. These devices include the thermoacoustic engine and thermoacoustic refrigerator. High-amplitude acoustic standing waves cause compression and expansion analogous to a Stirling power piston, while out-of-phase acoustic traveling waves cause displacement along a temperature gradient, analogous to a Stirling displacer piston. Thus a thermoacoustic device typically does not have a displacer, as found in a beta or gamma Stirling. Other developments. Starting in 1986, Infinia Corporation began developing both highly reliable pulsed free piston Stirling engines, and thermoacoustic coolers using related technology. The published design uses flexural bearings and hermetically sealed helium gas cycles, to achieve tested reliabilities exceeding 20 years. As of 2010, the corporation had amassed more than 30 patents, and developed a number of commercial products for both combined heat and power, and solar power. More recently, NASA has considered nuclear decay-heated Stirling engines for extended missions to the outer solar system. At the 2012 Cable-Tech Expo put on by the Society of Cable Telecommunications Engineers, Dean Kamen took the stage with Time Warner Cable Chief Technology Officer Mike LaJoy to announce a new initiative between his company Decca Research and the SCTE. Kamen refers to it as a Stirling engine. Theory. The idealized Stirling cycle consists of 4 thermodynamic processes acting on the working fluid. Isothermal expansion. The expansion space and associated heat exchanger are maintained at a constant high temperature, and the gas undergoes near isothermal expansion, absorbing heat from the hot source. Constant volume, known as isovolumetric or isochoric, heat removal. The gas is passed through the regenerator, where it cools, transferring heat to the regenerator for use in the next cycle. Isothermal compression. The compression space and associated heat exchanger are maintained at a constant low temperature, so the gas undergoes near isothermal compression, rejecting heat to the cold sink. Constant volume, known as isovolumetric or isochoric, heat addition. The gas passes back through the regenerator where it recovers much of the heat transferred in process 2, heating up on its way to the expansion space. Theoretical thermal efficiency equals that of the hypothetical Carnot cycle, i.e. the highest efficiency attainable by any heat engine. However, though it is useful for illustrating general principles, the ideal cycle deviates substantially from practical Stirling engines. It has been argued that its indiscriminate use in many standard books on engineering thermodynamics has done a disservice to the study of Stirling engines in general. Other real-world issues reduce the efficiency of actual engines, because of limits of convective heat transfer, and viscous flow, friction. There are also practical mechanical considerations. For instance, a simple kinematic linkage may be favored over a more complex mechanism needed to replicate the idealized cycle, and limitations imposed by available materials such as non-ideal properties of the working gas, thermal conductivity, tensile strength, creep, rupture strength, and melting point. A question that often arises is whether the ideal cycle with isothermal expansion and compression is in fact the correct ideal cycle to apply to the Stirling engine. Professor C.J. Rallis has pointed out that it is very difficult to imagine any condition where the expansion and compression spaces may approach isothermal behavior, and it is far more realistic to imagine these spaces as adiabatic. An ideal analysis where the expansion and compression spaces are taken to be adiabatic with isothermal heat exchangers and perfect regeneration was analyzed by Rallis and presented as a better ideal yardstick for Stirling machinery. He called this cycle the pseudo-Stirling cycle or ideal adiabatic Stirling cycle. An important consequence of this ideal cycle is that it does not predict Carnot efficiency. A further conclusion of this ideal cycle is that maximum efficiencies are found at lower compression ratios, a characteristic observed in real machines. In an independent work, T. Finkelstein also assumed adiabatic expansion and compression spaces in his analysis of Stirling machinery. Operation. Since the Stirling engine is a closed cycle, it contains a fixed mass.
Please subscribe and thanks for watching.